Gas-metal arc welding, sometimes referred to by its subtypes metal inert gas welding or metal active gas welding, is a welding process in which an electric arc forms between a consumable wire electrode and the workpiece metal, which heats the workpiece metal, causing them to melt and join. Along with the wire electrode, a shielding gas feeds through the welding gun, which shields the process from contaminants in the air. The process can be semi-automatic or automatic. A constant voltage, direct current power source is most commonly used with GMAW, but constant current systems, as well as alternating current, can be used. There are four primary methods of metal transfer in GMAW, called globular, short-circuiting, spray and pulse spray, each of which has distinct properties and corresponding advantages and limitations. Originally developed for welding aluminium and other non-ferrous materials in the 1940s, GMAW was soon applied to steels because it provided faster welding time compared to other welding processes. The cost of inert gas limited its use in steels until several years later, when the use of semi-inert gases such as carbon dioxide became common. Further developments during the 1950s and 1960s gave the process more versatility, and as a result, it became a highly used industrial process. Today, GMAW is the most common industrial welding process, preferred for its versatility, speed and the relative ease of adapting the process to robotic automation. Unlike welding processes that do not employ a shielding gas, such as shielded metal arc welding, it is rarely used outdoors or in other areas of air volatility. A related process, flux-cored arc welding, often does not use a shielding gas, but instead employs an electrode wire that is hollow and filled with flux. Development. The principles of gas-metal arc welding began to be understood in the early 19th century, after Humphrey Davy discovered the short-pulsed electric arcs in 1800. Vasily Petrov independently produced the continuous electric arc in 1802. It was not until the 1880s that the technology became developed with the aim of industrial usage. At first, carbon electrodes were used in carbon arc welding. By 1890, metal electrodes had been invented by Nikolai Slavyanov and C.L. Coffin. In 1920, an early predecessor of GMAW was invented by P.O. Nobel of General Electric. It used a bare electrode wire and direct current, and used arc voltage to regulate the feed rate. It did not use a shielding gas to protect the weld, as developments in welding atmospheres did not take place until later that decade. In 1926, another forerunner of GMAW was released, but it was not suitable for practical use. In 1948, GMAW was developed by the Battle Memorial Institute. It used a smaller diameter electrode and a constant voltage power source developed by H.E. Kennedy. It offered a higher deposition rate, but the high cost of inert gases limited its use to non-ferrous materials and prevented cost savings. In 1953, the use of carbon dioxide as a welding atmosphere was developed, and it quickly gained popularity in GMAW, since it made welding steel more economical. In 1958 and 1959, the short arc variation of GMAW was released, which increased welding versatility and made the welding of thin materials possible while relying on smaller electrode wires and more advanced power supplies. It quickly became the most popular GMAW variation. The spray arc transfer variation was developed in the early 1960s, when experimenters added small amounts of oxygen to inert gases. More recently, pulsed current has been applied, giving rise to a new method called the pulse spray arc variation. GMAW is one of the most popular welding methods, especially in industrial environments. It is used extensively by the sheet metal industry and, by extension, the automobile industry. The method is often used for arc spot welding, thereby replacing riveting or resistance spot welding. It is also popular for automated welding, in which robots handle the workpieces and the welding gun to speed up the manufacturing process. GMAW can be difficult to perform well outdoors, since drafts can dissipate the shielding gas and allow contaminants into the weld. Flux-cored arc welding is better suited for outdoor use, such as in construction. Likewise, GMAW's use of a shielding gas does not lend itself to underwater welding, which is more commonly performed via shielded metal arc welding, flux-cored arc welding, or gas tungsten arc welding. Equipment. To perform gas metal arc welding, the basic necessary equipment is a welding gun, a wire feed unit, a welding power supply, a welding electrode wire, and a shielding gas supply. Welding gun and wire feed unit. The typical GMAW welding gun has a number of key parts: a control switch, a contact tip, a power cable, a gas nozzle, an electrode conduit and liner, and a gas hose. The control switch, or trigger, when pressed by the operator, initiates the wire feed electric power and the shielding gas flow, causing an electric arc to be struck. The contact tip, normally made of copper and sometimes chemically treated to reduce spatter, is connected to the welding power source through the power cable and transmits the electrical energy to the electrode while directing it to the weld area. It must be firmly secured and properly sized, since it must allow the electrode to pass while maintaining electrical contact. On the way to the contact tip, the wire is protected and guided by the electrode conduit and liner, which help prevent buckling and maintain an uninterrupted wire feed. The gas nozzle directs the shielding gas evenly into the welding zone. Inconsistent flow may not adequately protect the weld area. Larger nozzles provide greater shielding gas flow, which is useful for high-current welding operations that develop a larger molten weld pool. A gas hose from the tanks of shielding gas supplies the gas to the nozzle. Sometimes, a water hose is also built into the welding gun, cooling the gun in high-heat operations. The wire feed unit supplies the electrode to the work, driving it through the conduit and onto the contact tip. Most models provide the wire at a constant feed rate, but more advanced machines can vary the feed rate in response to the arc length and voltage. Some wire feeders can reach feed rates as high as 30.5 meters per minute, but feed rates for semi-automatic GMAW typically range from 2 to 10 meters per minute. Tool style. The most common electrode holder is a semi-automatic air-cooled holder. Compressed air circulates through it to maintain moderate temperatures. It is used with lower current levels for welding lapper butt joints. The second most common type of electrode holder is semi-automatic water-cooled, where the only difference is that water takes the place of air. It uses higher current levels for welding T-corner joints. The third typical holder type is a water-cooled automatic electrode holder, which is typically used with automated equipment. Power supply. Most applications of gas metal arc welding use a constant voltage power supply. As a result, any change in arc length results in a large change in heat input and current. A shorter arc length causes a much greater heat input, which makes the wire electrode melt more quickly and thereby restore the original arc length. This helps operators keep the arc length consistent even when manually welding with handheld welding guns. To achieve a similar effect, sometimes a constant current power source is used in combination with an arc voltage-controlled wire feed unit. In this case, a change in arc length makes the wire feed rate adjust to maintain a relatively constant arc length. In rare circumstances, a constant current power source and a constant wire feed rate unit might be coupled, especially for the welding of metals with high thermal conductivities, such as aluminum. This grants the operator additional control over the heat input into the weld, but requires significant skill to perform successfully. Alternating current is rarely used with GMAW. Instead, direct current is employed and the electrode is generally positively charged. Since the anode tends to have a greater heat concentration, this results in faster melting of the feed wire, which increases weld penetration and welding speed. The polarity can be reversed only when special emissive coated electrode wires are used, but since these are not popular, a negatively charged electrode is rarely employed. Electrode selection is based primarily on the composition of the metal being welded, the process variation being used, joint design and the material surface conditions. Electrode selection greatly influences the mechanical properties of the weld and is a key factor of weld quality. In general, the finished weld metal should have mechanical properties similar to those of the base material with no defects such as discontinuities, entrained contaminants or porosity within the weld. To achieve these goals, a wide variety of electrodes exist. All commercially available electrodes contain deoxidizing metals such as silicon, manganese, titanium and aluminum in small percentages to help prevent oxygen porosity. Some contain denitriding metals such as titanium and zirconium to avoid nitrogen porosity. Depending on the process variation and base material being welded, the diameters of the electrodes used in GMAW typically range from 0.7 to 2.4 mm, but can be as large as 4 mm. The smallest electrodes, generally up to 1.14 mm, are associated with the short-circuiting metal transfer process, while the most common spray transfer process mode electrodes are usually at least 0.9 mm. Shielding gases are necessary for gas-metal arc welding to protect the welding area from atmospheric gases such as nitrogen and oxygen, which can cause fusion defects, porosity, and weld metal embrittlement if they come in contact with the electrode, the arc, or the welding metal. This problem is common to all arc welding processes. For example, in the older shielded metal arc welding process, the electrode is coated with a solid flux which evolves a protective cloud of carbon dioxide when melted by the arc. In GMAW, however, the electrode wire does not have a flux coating, and a separate shielding gas is employed to protect the weld. This eliminates slag, the hard residue from the flux that builds up after welding and must be chipped off to reveal the completed weld. The choice of a shielding gas depends on several factors, most importantly the type of material being welded and the process variation being used. Pure inert gases such as argon and helium are only used for non-ferrous welding. With steel, they do not provide adequate weld penetration or cause an erratic arc and encourage spatter. Pure carbon dioxide, on the other hand, allows for deep penetration welds but encourages oxide formation, which adversely affect the mechanical properties of the weld. LTS low cost makes it an attractive choice, but because of the reactivity of the arc plasma, spatter is unavoidable and welding thin materials is difficult. As a result, argon and carbon dioxide are frequently mixed in a 75%, 25% to 90%, 10% mixture, generally in short-circuit GMAW. Higher carbon dioxide content increases the weld heat and energy when all other weld parameters are held the same. As the carbon dioxide content increases over 20%, spray transfer GMAW becomes increasingly problematic, especially with smaller electrode diameters. Argon is also commonly mixed with other gases: oxygen, helium, hydrogen and nitrogen. The addition of up to 5% oxygen can be helpful in welding stainless steel. However, in most applications carbon dioxide is preferred. Increased oxygen makes the shielding gas oxidize the electrode, which can lead to porosity in the deposit if the electrode does not contain sufficient deoxidizers. Excessive oxygen, especially when used in application for which it is not prescribed, can lead to brittleness in the heat-affected zone. Argon-helium mixtures are extremely inert and can be used on non-ferrous materials. A helium concentration of 50 to 75% raises the required voltage and increases the heat in the arc due to helium's higher ionization temperature. Hydrogen is sometimes added to argon in small concentrations for welding nickel and thick stainless steel workpieces. In higher concentrations, it may be used for welding conductive materials such as copper. However, it should not be used on steel, aluminum or magnesium because it can cause porosity and hydrogen embrittlement. Shielding gas mixtures of 3 or more gases are also available. Mixtures of argon, carbon dioxide and oxygen are marketed for welding steels. Other mixtures add a small amount of helium to argon-oxygen combinations. These mixtures are claimed to allow higher arc voltages and welding speed. Helium also sometimes serves as the base gas, with small amounts of argon and carbon dioxide added. However, because it is less dense than air, helium is less effective at shielding the weld than argon, which is denser than air. It also can lead to arc stability and penetration issues, and increased spatter due to its much more energetic arc plasma. Helium is also substantially more expensive than other shielding gases. Other specialized and often proprietary gas mixtures claim even greater benefits for specific applications. The desirable rate of shielding gas flow depends primarily on weld geometry, speed, current, the type of gas, and the metal transfer mode. Welding flat surfaces requires higher flow than welding grooved materials, since gas disperses more quickly. Faster welding speeds, in general, mean that more gas must be supplied to provide adequate coverage. Additionally, higher current requires greater flow, and generally, more helium is required to provide adequate coverage than if argon is used. Perhaps most importantly, the 4 primary variations of GMAW have differing shielding gas flow requirements for the small weld pools of the short-circuiting and pulsed spray modes. About 10 L per minute is generally suitable, whereas for globular transfer around 15 L per minute is preferred. The spray transfer variation normally requires more shielding gas flow because of its higher heat input and thus larger weld pool. Typical gas flow amounts are approximately 20 to 25 L per minute. Flux cord wire-fed flux cord self-shielding. A gasless wire-fed welding had been developed for simplicity and portability. This avoids the gas system of conventional GMAW and uses a cord wire containing a solid flux. This flux vaporizes during welding and produces a plume of shielding gas. Although described as a flux, this compound has little activity and acts mostly as an inert shield. The wire is of slightly larger diameter than for a comparable gas-shielded weld, to allow room for the flux. The smallest available is 0.8 mm diameter, compared to 0.6 mm for solid wire. The shield vapor is slightly active, rather than inert, so the process is always MAGS but not MIG. This limits the process to steel and not aluminium. Vaporizing the additional flux requires greater heat in the wire, so these gasless machines operate as DCEP, rather than the DCEN usually used for GMAW to give deeper penetration. DCEP, or DC electrode positive, makes the welding wire into the positively charged anode, which is the hotter side of the arc. Provided that it is switchable from DCEN to DCEP, a gas-shielded wire feed machine may also be used for flux-cord wire. Flux-cord wire is considered to have some advantages for outdoor welding on site, as the shielding gas plume is less likely to be blown away in a wind than shield gas from a conventional nozzle. A slight drawback is that, like GMAW welding, there may be some flux deposited over the weld bead, requiring more of a cleaning process between passes. Flux-cord welding machines are most popular at the hobbyist level, as the machines are slightly simpler but mainly because they avoid the cost of providing shield gas, either through a rented cylinder or with the high cost of disposable cylinders. GMAW-based 3D printing. GMAW has also been used a low-cost method to 3D print metal objects. Various open-source 3D printers have been developed to use GMAW. Such components fabricated from aluminum compete with more traditionally manufactured components on mechanical strength. By forming a butt weld on the first layer, GMAW 3D printed parts can be removed from the substrate with a hammer operation. For most of its applications, gas metal arc welding is a fairly simple welding process to learn, requiring no more than a week or two to master basic welding technique. Even when welding is performed by well-trained operators, weld quality can fluctuate since it depends on a number of external factors. All GMAW is dangerous, though perhaps less so than some other welding methods, such as shielded metal arc welding technique. The basic technique for GMAW is quite simple, since the electrode is fed automatically through the torch. By contrast, in gas tungsten arc welding, the welder must handle a welding torch in one hand and a separate filler wire in the other. And in shielded metal arc welding, the operator must frequently chip off slag and change welding electrodes. GMAW requires only that the operator guide the welding gun with proper position and orientation along the area being welded. Keeping a consistent contact tip to work distance is important, because a long stick-out distance can cause the electrode to overheat and also wastes shielding gas. Stick-out distance varies for different GMAW weld processes and applications. The orientation of the gun is also important. It should be held so as to bisect the angle between the workpieces, that is, at 45 degrees for a fillet weld and 90 degrees for welding a flat surface. The travel angle, or lead angle, is the angle of the torch with respect to the direction of travel, and it should generally remain approximately vertical. However, the desirable angle changes somewhat depending on the type of shielding gas used. With pure inert gases, the bottom of the torch is often slightly in front of the upper section, while the opposite is true when the welding atmosphere is carbon dioxide. Quality. Two of the most prevalent quality problems in GMAW are dross and porosity. If not controlled, they can lead to weaker, less ductile welds. Dross is an especially common problem in aluminium GMAW welds, normally coming from particles of aluminium oxide or aluminum nitride present in the electrode or base materials. Electrodes and workpieces must be brushed with a wire brush or chemically treated to remove oxides on the surface. Any oxygen in contact with the weld pool, whether from the atmosphere or the shielding gas, causes dross as well. As a result, sufficient flow of inert shielding gases is necessary, and welding in volatile air should be avoided. In GMAW, the primary cause of porosity is gas entrapment in the weld pool, which occurs when the metal solidifies before the gas escapes. The gas can come from impurities in the shielding gas or on the workpiece, as well as from an excessively long or violent arc. Generally, the amount of gas entrapped is directly related to the cooling rate of the weld pool. Because of its higher thermal conductivity, aluminum welds are especially susceptible to greater cooling rates and thus additional porosity. To reduce it, the workpiece and electrode should be clean, the welding speed diminished and the current set high enough to provide sufficient heat input and stable metal transfer, but low enough that the arc remains steady. Preheating can also help reduce the cooling rate, in some cases by reducing the temperature gradient between the weld area and the base material. Safety gas metal arc welding can be dangerous if proper precautions are not taken. Since GMAW employs an electric arc, welders wear protective clothing, including heavy leather gloves and protective long-sleeve jackets, to avoid exposure to extreme heat and flames. In addition, the brightness of the electric arc is a source of the condition known as arc eye, an inflammation of the cornea caused by ultraviolet light and, in prolonged exposure, possible burning of the retina in the eye. Conventional welding helmets contain dark faceplates to prevent this exposure. Newer helmet designs feature a liquid crystal-type faceplate that self-darken upon exposure to high amounts of UV light. Transparent welding curtains, made of a polyvinyl chloride plastic film, are often used to shield nearby workers and bystanders from exposure to the UV light from the electric arc. Welders are also often exposed to dangerous gases and particulate matter. GMAW produces smoke-containing particles of various types of oxides, and the size of the particles in question tends to influence the toxicity of the fumes, with smaller particles presenting a greater danger. Additionally, carbon dioxide and ozone gases can prove dangerous if ventilation is inadequate. Furthermore, because the use of compressed gases in GMAW pose an explosion and fire risk, some common precautions include limiting the amount of oxygen in the air and keeping combustible materials away from the workplace.